The subject of the current video is Tikhonov regularization. Before we discuss the details of Tikhonov regularization, let's remind ourselves about regularization in general. Regularization is the term given to the means through which we obtain a unique solution to an ill-posed inverse problem. However, it's not just uniqueness we seek. We seek uniqueness specifically through obtaining a minimum error variance solution to that inverse problem. So, when we're calibrating a groundwater model, which is always a fundamentally ill-posed inverse problem because of the heterogeneous nature of the media through which water flows, we then, having calibrated a model using regularization in the correct way, if we do it in the correct way, we will then be able to make predictions which are of minimized error variance. These predictions will not be correct because there's uncertainty born of non-uniqueness of the ill-posed problem which has to be solved when that model is calibrated. However, predictions will be of minimized error variance because the potential for error in those predictions will have been made roughly symmetrical about the predictions that we're making. So, to set a context for our discussions of Tikhonov regularization, let's begin by showing an example of an ill-posed inverse problem, and then we can discuss the mechanisms through which Tikhonov regularization is applied in solution to that problem. So here's a model domain, and into the right-hand side of that model domain, water flows at a rate Q, 1 cubic meters per meter per day. Let's assume that this is a confined aquifer, and that the 8 parameters that I am trying to estimate are resistances in each of 8 segments of the model domain. I'm defining resistance as the inverse of transmissivity. I'm setting the head at a fixed value at the left of the model domain, a fixed value of 0. The head is H1 in this well, H2 in this well, and these two heads together comprise my observation data set. So I am attempting to estimate 8 parameters on the basis of 2 measurements of head. This, of course, is a problem which is ill-posed. Nevertheless, it resembles many of the problems with which we're faced when we're calibrating a groundwater model, because the medium through which water flows is heterogeneous at every scale. Properties are different in every place. We have a limited data set available for calibration. We are faced with this same type of problem, but in 2 or 3 dimensions, and not just the 1 dimension illustrated in this example. So I'm going to use the same equation to characterize this problem as that which I've used in other videos. H equals zk plus epsilon. What I observe, H, is the action of the model on the parameters, represented by the action of a matrix on a vector, plus measurement noise. In this case, the vector H has 2 elements, H1 and H2. The vector K has 8 elements, R1 to R8, and each one of those R1 to R8 is represented in the vector K. So Ki, ith element of K, is the ith resistance in my model domain. Now, obviously this problem is ill-posed, and one can see just by looking at it that as long as R1 and R4 sum to H1 and R5 and R8, R5 to R8 sum to H2 minus H1, then that is a solution to that inverse problem. That leaves 6 degrees of freedom to solve that problem, because there are an infinite number of ways in which I can select R1 to R8 such that R1 plus R2 plus R3 plus R4 equals H1, and R5 plus R6 plus R7 plus R8 equals H2 minus H1. So here's my equation again, which represents the inverse problem which I am trying to solve. And I'll represent the vectors and matrices in these equations figuratively using this diagram. The matrix H is long in the horizontal direction, and as such the problem is ill-posed, because any matrix that is long in the horizontal direction has a null space, and when a matrix has a null space, the inverse problem, which is based on that matrix, is ill-posed. Of course, many matrices that are long in the vertical direction can also have a null space, and whenever there's a null space, there is problem ill-posedness. The null space was discussed in another video. Specifically, our inverse problem is written in this way: H1, H2, 4 ones in the top row of the Z matrix, 8 ones in the bottom. Here's our parameters that we want to estimate. There's measurement noise. Now let's regularize this inverse problem. So here's my equation that defines that inverse problem, and here is my representation of the vectors and matrices that are involved in this problem. Now I'm going to supplement these vectors and matrices with another set of vectors and matrices. I'm going to refer to these using the equation A equals Tk plus neta, where T is a matrix that expresses my so-called regularization constraints. This set of equations, expressed by this matrix equation, provides a value for each parameter, or a value for relationships between parameters. We'll see some examples shortly. This information embodied in this equation pertains directly to the parameters that I'm trying to estimate. Where do these relationships come from? Expert knowledge, perhaps through direct measurements of system properties. In either case, information that pertains directly to the parameters are recorded in this equation. Now, to obtain uniqueness of solution to that inverse problem, all parameters should be involved in a relationship. Hence, the number of rows in that T matrix should equal at least the number of parameters that I'm trying to estimate, that is, the number of columns in the T matrix. It should be square, or it should be long in the vertical direction. So let me join these two matrix equations together to form a single matrix equation with a matrix that is now long in the vertical direction, and hence I'm satisfying a necessary but not necessarily sufficient wrong way around. This is it's a necessary but not sufficient condition for this inverse problem to be well posed, because I am supplementing the calibration data set with a suite of other relationships which pertain directly to the parameters that I am trying to estimate. So what this is doing now, it's providing a fallback position for all parameters. Through bringing the T matrix and the relationships embodied in the A equals Tk plus neta matrix equation, I am saying that if there is no information to the contrary in the calibration dataset, we have a place where parameters can go. We have a fallback position. That is, the set of values or the set of relationships embodied in the regularization equations with which the inverse problem has now been supplemented. And in ways we'll describe later in this video, I seek uniqueness of solution of that inverse problem by specifying that the parameters that I estimate shall depart from their fallback position to the minimum extent required to fit the calibration dataset. Hence, I attain uniqueness. Out of all the many ways to fit the two heads in the example which we're talking about in this video, of all the many ways for the R1 to R8 to fit the data, I want the way that minimize departure from a preferred parameter condition that is defined through that T matrix. Now there are a number of ways we can do this. I call preferred value regularization when our T matrix looks like this. 1's just down the diagonals and 0 off diagonal elements. What T matrix specifies in this case is that each parameter has a value equal to the corresponding element of this A vector. So R1, our first resistance, is equal to A1, R2 is equal to A2, etc. So the fallback position in this case is simply a value assigned to each parameter. R1, R2, R3 all have a fallback position which is a value provided specifically to them, which can be the same value, in which case homogeneity is the preferred system condition from which we seek minimum departure to solve the inverse problem. Another option which also says that homogeneity is the preferred condition, I call preferred difference regularization. Here I'm not actually specifying a preferred value for every parameter, but I am specifying the fact that the difference in the values between each parameter and its neighbor shall be 0. So the fallback position is that R1 minus R2 is 0. That is, that R1 equals R2. Now, probably R1 does not equal R2. However, I'm saying that to the extent which R1 has to differ from R2 in order for collectively R1 to R8 to provide a good fit with H1 and H2, the set of parameters that we come up with to provide that fit out of all the million possibilities is that which provides minimum departure from homogeneity specified through the T matrix, each row of which has a 1 and a negative 1 in the respective row and zeros elsewhere. And we can get more complicated. We may, for example, suggest minimum curvature regularization. In this case, we're saying, yes, R1 and R2 will be different, and R2 and R3 will be different, but the differences of the differences have to be minimized. Which one should we use? That will depend on the situation, and it should be a reflection of expert knowledge. And if our Tikhonov constraints encapsulated in that T matrix are an expression of expert knowledge, this then provides us with a solution to the inverse problem which is in maximum accordance with expert knowledge, which departs from expert knowledge to the minimum amount required for the parameters to allow a good fit to be attained with the calibration data set. Now, this neta vector here, It has a similar role to measurement noise. Regardless of whether we are using minimum curvature, preferred difference, or preferred value, there is a neta in this equation, whereby we recognize that these values or these conditions that we apply through our Tikhonov constraints, they're not absolutely rigid conditions, they're suggestions. We recognize that we're probably wrong because we'll probably need to introduce heterogeneity into the model domain to allow a good fit to be attained between model outputs and the calibration data set. Neta then is an expression of our uncertainty in the relationships which we supply as Tikhonov constraints. The greater the departure from the preferred condition, the preferred values or the preferred differences, the bigger the penalty in that part of the objective function which applies to Tikhonov constraints. We'll discuss that shortly. This then takes the role, as I said previously, of measurement noise. The greater the certainty that I have that a particular parameter has a certain value, or the difference between two parameters is 0, the greater the weight that I will give that particular observation. I'll call it a regularization observation. The greater the weight, the more certain I am that that particular constraint applies. And the weight is the inverse of the uncertainty associated with that. Large weight, small uncertainty, small value for neta, that is the uncertainty applied to that regularization constraint. Now let's formalize this with a set of equations. So here's our problem defining equation. The noise associated with the data, the uncertainties associated with my Tikhonov constraints. I'll define two Q matrices, two weight matrices, as I've done in other slideshows, other videos. QM ideally should be the inverse of the covariance matrix of measurement noise. Because measurement noise is normally independent from measurement to measurement, C epsilon, our covariance matrix of measurement noise, is normally a diagonal matrix. QM, the inverse of C epsilon, will therefore normally also be a diagonal matrix. The same, as we'll talk about shortly, does not necessarily apply to neta. The uncertainty pertaining to our preferred parameter conditions will often show correlation, particularly if our parameters have a spatial disposition, as they do for the R1, R2 parameters that are the example that we're discussing. In that case, C neta will not necessarily be a diagonal matrix, and QR, therefore, will not necessarily be a diagonal matrix. So, to solve our inverse problem, we define an objective function and then we minimize it. Here is the objective function that we define. It is the sum of squared residuals, as in other videos that we've discussed. In this case, the objective function has two components. There is the sum of squared weighted residuals between model outputs and corresponding measurements. And there is the sum of squared weighted residuals between regularization relationships and the observed values of those relationships, that is, the values encapsulated in this A vector. So to the extent to which parameters need to depart from their preferred condition to fit the calibration data set, the regularization objective function rises. to the extent to which measurements are not matched by model outputs, the measurement objective function rises. The two summed together is the objective function that I minimize. Now, if we write these equations slightly differently, if we define M as the combination of the H and A vectors, if we define the Y matrix as the combination of the Z and T matrices, and if we define the Tor vector as the combination of the epsilon and neta vectors, and if we define a composite weight matrix through putting each of these inverse of various covariance matrices on the diagonal of a composite Q matrix, we end up with this equation. And in other videos we've seen this equation. And if the problem is well posed, if Tikhonov regularization has achieved its end, the solution to the objective function minimization problem we have shown in other videos is given by this equation. Our estimated set of parameters k underscore ytqy to the negative 1 ytqm, and we are hoping that that negative 1 exists, that this matrix does indeed have an inverse. We can, so here's our solution to the inverse problem. We can rewrite that solution in terms of our original matrices, so by substituting the matrices that define each one of the matrices that appear in this equation, we obtain this equation for k underscore, and if we do all the matrix multiplications we end up with this equation. K hat equals all those terms on the right. And if A equals 0, as it often does through the way in which we define preferred conditions for the parameters, or we redefine our parameters to ensure that A equals 0, we can leave off this term and this equation becomes this equation. This is a little bit easier to manipulate if A is 0. This then becomes our solution to the inverse problem. This is our k underscore. However, we've got a bit of a problem here. Yes, we want to attain a minimum error variance solution to the inverse problem. We want to obtain numerical stability. We want to obtain a good fit with the calibration data set, but we don't want to overfit. We have a problem of how to balance the weights that we assign to the measurements against the weights that we assign to the regularization observations, the regularization constraints. The weights are embodied in the QM and the QR matrices. Now, ideally, as we have discussed, QM should be proportional to the inverse of the covariance matrix of measurement noise. But it's more than measurement noise that causes model-to-measurement misfit. It's also structural noise, the imperfections of the model. We don't actually know C epsilon. And what's the uncertainty of the regularization constraints? We don't actually know those either. So we can't actually define QM and QR in such a way that these two are balanced the way they should be balanced, to balance model to measurement misfit against adherence to regularization constraints. If we get that balance wrong, we will not attain the things we desire. We will not attain necessarily numerical stability. This matrix might not be invertible, or it might border on singularity. Or if we give too much weight to the regularization constraints, we might not get a good fit with the calibration data set. So we have the problem of balancing this against this in order to attain the goals we seek through regularization. Fortunately, this problem can be solved fairly easily if we redefine the inversion problem. And we redefine it as a constrained minimization problem. We say that we want to minimize the regularization objective function subject to the constraint that the measurement objective function is a value which we supply, which I'm calling phi t, a target measurement objective function. Now, I'm assuming here that we can attain that target. I'm assuming that we have enough parameters and the model is good enough for us to attain whatever measurement objective function we want. In practice, we mightn't attain it. But let's assume for the moment we can. What we are saying then is that we do not want to fit any better than a level of fit which we state before we start the inversion process. Achieve this level of fit, but no better, and in doing that, give me the minimum perturbation from the preferred parameter condition in order to achieve that fit. Now, perhaps if our model is really good and it's measurement noise that determines the misfit, we can calculate the target measurement objective function up front just based on what we know about measurement noise. More often than not, we can't do that. More often than not, we'll get as good a fit which we can with the calibration data set, and then say, well, that's too good a fit. I now know how good an objective function I can get. I'll set my target measurement objective function, say 5% greater than that, undertake the inversion process again, and set my target accordingly. As I said, perhaps 5-10% greater than the fit I know I can get, and that last 5 to 10% will give me probably a parameter field that I like a lot better than the overfitted parameter field which I previously achieved. We can use Tikhonov regularization to get as good a fit as possible in ways that are available through PEST. For example, I can tell PEST to set the target measurement objective function always at about, for example, 10% of the current measurement objective function. That'll be discussed in another video. And I can get a pretty good solution to that inverse problem through doing that, but the fit will probably still be too good and the parameter field probably a little bit too rough because of that. So in most cases, either by previously obtaining too good a fit with the calibration data set and then deciding to fit to a target that's 5% above that, or through knowing what that target should be on theoretical grounds, I can come up with a suitable phi t and therefore pose the inverse problem as a constrained minimization problem through which not only do I attain uniqueness, but I obtain uniqueness in a nice way, a way that gives me minimum error variance through maximizing my adherence to a preferred parameter condition which encapsulates my expert knowledge. So how do I do this balance then? I do this by incorporating a new variable beta squared into the objective function that I minimize. I'm now balancing phi m against phi r by seeking that a condition wherein phi m equals the target measurement objective function, that is phi t. And through solving the inverse problem in a way that enables me to estimate beta squared such that phi m equals phi t, I've attained my objective. So the equations I had before now include beta squared. And during each iteration of the constrained optimization process, which is used to solve the non-unique inverse problem, during each iteration, beta squared is adjusted in a way that guarantees that phi m will equal phi t, or at least get closer to it at the end of that iteration. It probably won't attain it in one iteration because the model's non-linear, but we will guarantee that we will get a phi m that is equal to phi t but no lower. And in so doing, we don't overfit. And in so doing, we attain uniqueness of the inverse problem. So this then is a very pleasing outcome. We've attained uniqueness, and we've attained uniqueness in a way that we like, because we have specified what we like through the Tikhonov constraints. And by insisting that we depart from what we like to the minimum extent required to fit the calibration data set, we have obtained uniqueness in a way that is pleasing, a way that is minimum error variance. However, it's important to realize that there are two components really to the way that Tikhonov regularization operates. We seek minimum departure from a preferred parameter condition. But it's not just the fact that we minimize that departure that's important. It's also the way in which we deviate from that preferred condition that is also important. We will have to deviate from that preferred condition if it's a condition of homogeneity or a condition that each parameter has a preferred value. By deviating from that condition to the smallest extent necessary to fit the data, and through deviating from that condition in a way that is pleasing, in a way that is in accordance with the underlying geology or our underlying conception of geology, that also provides part of that minimum error variance guarantee. Hence, the importance of this QR matrix. This is what determines the way in which we depart from the minimum error variance, the way in which we depart from the preferred conditions for parameters encapsulated in Tikhonov constraints. So let me show an example here. Here's the problem that we're using as an example. And let us suppose that we know that there is spatial correlation between these hydraulic properties. We might know, for geological reasons, that if R1 has a high value, then R2 is likely to be high, and R3 is likely to be high just because of the nature of the geology at this site. Suppose that this is only part of a much larger model domain, and that we know that spatial correlation between parameters is likely to exist over a significant part of that model domain, which I'll specify diagrammatically through this arrow here. Suppose then that the C neta matrix, which specifies the uncertainties associated with my preferred parameter condition, needs to exhibit spatial correlation over this length. It will have off-diagonal elements, hence the QR matrix used in the Tikhonov constraints, the QR matrix used in defining the regularization objective function, must also have off-diagonal elements which respect this degree of spatial correlation. In doing so, we're saying, should heterogeneity need to arise, it must arise in a way that respects that spatial correlation if it can. So, suppose this is our situation. Suppose we're using preferred value Tikhonov regularization. And suppose that the preferred value for all our parameters is this line here. Suppose also that in this particular case, the real value of the parameters, which I'll never know, are expressed by this pattern. Now obviously none of them agree with the preferred value of the parameters, so we will have to depart from those preferred values. Now suppose that I were to use a QR matrix which is simply proportional to the identity matrix. I will probably attain a solution to that inverse problem which looks like this dark line. I'll get the fit I want with the calibration data set. I'll achieve my target measurement objective function, but I'll do so in a way that is, by fitting H1, I fit it fairly independently of how I get a good fit with H2. So I'll have probably homogeneity here, independently of what happens here. Alternatively, suppose I use a QR matrix that is indeed proportional to the inverse of the C-neta matrix, which thereby respects the fact that I want my solution to the inverse problem to exhibit spatial correlation in a way that I've defined through C-neta. Then my solution to the inverse problem will probably be more like this. I'll still achieve my target measurement objective function, but I will achieve it in a way that is much more in accordance with what I believe the underlying geology to be. So the choice of this QR matrix is important when applying Tikhonov regularization. We remember that it's not just the fact that we want to depart minimally from a preferred parameter condition that gives us a minimum error variance solution to the inverse problem. It's the fact that we want to depart in a way that makes most sense in terms of how we think the disposition of hydraulic properties is like under our site, that is important. If we just say that each component, each regularization constraint has a weight and not a covariance matrix, that is, we give Q, we make QR a diagonal matrix, then we'll probably do what's often called point-by-point fitting. We'll get a good fit, and only the parameters that are most sensitive to each observation will be varied to give us that good fit, and any relationship that we would like their variability to have with neighbouring parts of the model domain is ignored. That situation is easily rectified by defining our QR matrix on the basis of a spatial correlation which we know to exist or we would like to exist in our calibrated parameter field, and therefore the parameter field that emerges through the history matching process will show spatial continuity in ways that we will like, and we will not get a blotchy point-by-point fit with the data. We will get a fit that makes sense to us geologically, is much more pleasing, and hence has a much greater claim to the status of minimum error variance solution to the inverse problem which we are solving using Tikhonov regularization. In other videos we discussed the resolution matrix. This is the matrix that links the parameter field that we estimate through solution of an inverse problem with the parameter field that exists in reality, that is, real-world hydraulic properties. Just as for other methods of regularization, we can derive a resolution matrix for Tikhonov regularization. So here's the equation which describes our linearized version of reality. And here are the solutions we obtained for our estimated parameter field, K underscore, when we estimated that parameter field using Tikhonov regularization. Let's now substitute this equation into this equation for H. And through very basic matrix manipulation, we obtain this equation for K underscore, which we can express as K underscore equals RK plus G epsilon, where R equals GZ. This is the resolution matrix. Remember that each row of the resolution matrix expresses the averaging relationship through which an individual element of K hat is derived from the K that exists in reality. To the extent that the resolution matrix differs from the identity matrix, the estimated parameter field is a simplified version of the real parameter field, this simplification being necessary for the attainment of uniqueness of the ill-posed inverse problem. I'd like to say a few words about the relationship between Tikhonov regularization and singular value decomposition. So I'm going to repeat the equations that we showed before, where Tikhonov regularization is used as our solution mechanism for the inverse problem to derive a K underscore vector, which is the solution for that problem. These equations require that a matrix be inverted. Now, Tikhonov regularization ideally should make that matrix invertible. In practice, in difficult inversion settings, many of which arise in calibration of a groundwater model, that matrix may not be invertible or may be nearly singular and may be difficult to invert numerically. Always, we should, when solving that equation to obtain K hat, we should always use singular value decomposition, because for reasons discussed in other videos, singular value decomposition will always work even if there's a matrix there which is singular or near singular. In practice, we may not use exactly this equation, but an equation that's similar to it and achieves the same thing, but is based on singular value decomposition or a method that is closely related to it. There's another interesting matter that's worth discussing, and that's the relationship between Tikhonov regularization and singular value decomposition. It can be shown that if certain conditions are met, They achieve the same thing in solution of an ill-posed inverse problem. In particular, if reality can be described by a CK covariance matrix, which we know, if we base our Q matrix, our QR matrix through which we implement Tikhonov regularization on that CK matrix and solve for K underscore, our estimated parameter field, we obtain the same K underscore, the same solution to the inverse problem, as that which we would have achieved if we had undertaken singular value decomposition based on a Cahunin-Louvre transformation that was implemented on the basis of that same CK matrix. The solutions converge as measurement noise approaches zero. So that's a rather satisfying thing to know. In the limit, they both give us the same thing. Why then would we use Tikhonov rather than singular value decomposition to achieve our minimum error variance solution to the inverse problem? The reason is because Tikhonov regularization is so much more flexible. We have so many options for how we formulate that T matrix, which provides the Tikhonov constraints. We can use preferred value, preferred difference, minimum curvature, as we've discussed. But there are many other options as well. And all of them really should be used, or any option that we use, should be designed to express what we know. Even though we don't know it exactly, we would like, this is our ability to exert some pressure on the inversion process so that the solution to the inverse problem is as much in accordance as what we would like it to be as possible. We may, for example, suggest through an appropriate Tikhonov matrix that if heterogeneity needs to arise in the calibrated parameter field, that it arise close to some feature that we think may actually have heterogeneous hydraulic properties. And we may suggest that if it arises, it have continuity in certain directions. In theory, this can all be embodied in a linear or nonlinear Tikhonov set of constraints in a Tikhonov matrix, or a nonlinear equivalent of that matrix. Sharpness filters, so that we can say, for example, that if heterogeneity arises at a certain place, we would like the boundary between the two different property values to be rather sharp rather than smooth. All of these options are open to us if we seek solution to the ill-posed inverse problem using Tikhonov constraints. The other nice thing about the Tikhonov mechanism for solution of the inverse problem is the way that we can adapt to the presence of measurement noise. There's a lever, the target measurement objective function. If we set it too low, we overfit. We get bumps and lumps in the parameter field. It doesn't look good. If we set it too high, we don't get as much information out of the calibration data set as we should. We don't get as good a fit as we should. It's not too hard to find an appropriate value for the target measurement objective function. So we've got a lever here which works. With singular value decomposition, it's not quite the same. Our lever there is the truncation point, the number of singular values that we use to separate solution space from null space. It is harder to find the correct value for the truncation point, and everything is based on a Cahunin-Louvre transformation which hardwires in our pre-selection of what heterogeneity should look like. There's little room for surprise if parameters heterogeneity arises in certain places and in ways we didn't expect. Tikhonov allows that to happen. Hence it's more flexible and more accommodating, not just of what we know about the subsurface, but of what we don't know and may surprise us. Hence, as stated elsewhere, Tikhonov regularization is our pathway to a minimum error variance solution to the inverse problem. Singular value decomposition should be used to solve the equations that Tikhonov regularization sets up for us. now like to discuss an example that illustrates the interplay between the measurement objective function and the regularization objective function. In this example, I actually use the ModFlow groundwater model to interpret resistivity data. This is geophysical data. Without going into too many details, this data is acquired by passing current into the ground through one electrode, out of the ground through another electrode, and then measuring voltage between other pairs of electrodes scattered over the surface of the Earth. And then I interchange the roles of the current and voltage electrodes many times to obtain many different dispositions of voltage and current electrode pairs. I amass a whole lot of data in this way, a whole lot of voltage measurements based on current measurements, and from that data I try to infer the distribution of resistivity in the subsurface. This type of model is in fact very similar to a groundwater model. Direct current, direct flow of electric current obeys Laplace's equation, just like steady state flow of groundwater. In this case, here's a situation statement. I have 120,000 parameters. The Jacobian matrix is not obtained through finite differences. It's obtained using an adjoint state solution of the equations using the model that actually computes the flow of current through the ground. And my regularization is achieved using three-dimensional minimum curvature constraints. This is the equation that's employed in the T matrix employed by Tikhonov regularization. Now in this case I'm going to, as I said, look at the interplay between the measurement and regularization objective functions. I'm going to minimize the total objective function, and I'm going to commence that minimization process by assigning all measurements a weight of 0. So at the start of this sequence of slides that we're about to see, we start off with only Tikhonov regularization applying. The solution to that problem is homogeneity of the inferred parameter field. Then I slowly will put more and more weight on the data, and we will see heterogeneity appear as the composition of the total objective function thereby changes. So here's where we start off, where the solution of the inverse problem is homogeneous parameter field because that inverse problem is posed with only Tikhonov regularization, and I get a perfect fit with my regularization objective function if there is no heterogeneity whatsoever in any part of the model domain. I then slowly increase the weight on the measure associated with the field measurements. And as I do, we can see heterogeneity begin to appear. We see departures from homogeneity appear, constrained to appear in a 3D minimum curvature sense. So it's smooth apparition of the heterogeneity. So I put more weight on the data, a little bit more detail of what may be under the surface appears through solution of the inverse problem. All the while I'm getting a better fit with that data. At some stage, however, I say that's a good enough fit. There's heterogeneity appearing on the surface here and little parts down here, which is unrealistic. At this stage, I'm probably overfitting. Now, if I took that sequence of solutions to the inverse problem and plotted the value of the regularization objective function as a function of the value of the measurement objective function, I'd obtain a curve like this, which is often referred to as the L curve. This is where I started off, that sequence of slides which we just saw. My regularization objective function was 0, because the parameter field, the estimated parameter field, was perfectly homogeneous. As I added more and more weight to the data, the measurement objective function fell. It falls quite fast because just a little bit of weight on that data allows me to achieve a much better fit than that achieved using a homogeneous parameter field. And heterogeneity starts to appear in the subsurface, as you just saw. Eventually I get to a point here where trying to get a better fit costs me heavily in terms of deviating from the preferred condition of homogeneity and the preferred constraint of minimum curvature. Getting that last bit of fit causes a lot of bumps and lumps to appear in that parameter field, a lot of which are suspicious. Do they really reflect reality, or am I fitting noise in the data, or is the model inadequate and that noise that I'm fitting is actually structural noise incurred by the fact that the model is not a perfect simulator of what happens under the ground? It seems intuitive then that the best place to call my model fit, the best place to say that I've achieved a minimum error variance solution of the inverse problem is this point here, the point just before things start to get bad in terms of introducing heterogeneity to the parameter field, which is probably spurious. And in geophysical data interpretation, this is often the place where it is said the best solution is obtained. This point where we've extracted information from the data but haven't tried to extract more information than we have the ability to extract because that information is too polluted with measurement or structural noise. And that illustrates something that I also said previously, that it's that last 5 to 10% of the fit that gives us the potential for spurious heterogeneity to arise in the estimated parameter field. That we can get a good fit, but seeking too good a fit rapidly deteriorates, causes deterioration in the solution to the inverse problem. Now I'm going to present another sequence of slides where I solve the inverse problem again using Tikhonov regularization, but in this case my T matrix has horizontal minimum curvature constraints and not a vertical minimum curvature constraint. So same data, same level of fit, same process of putting more and more weight on the data and deviating more and more from the preferred condition of parameter homogeneity, but in this case the Tikhonov constraints are different. As we go through the sequence of slides, we see heterogeneity arise just as before, but in this case it arises at much shallower depths. And what this illustrates is that the solution to the inverse problem is going to depend very much on the regularization that we use. The inverse problem is ill-posed. That means there's a lot of different combinations of parameters that can fit the data. Which is the best? Well, we decide which is the best through the way in which we implement Tikhonov regularization. Which is the best in this particular case? Is it that parameter field or is it that parameter field? That is for us to decide, not the mathematics. It is then incumbent on us to supply a set of Tikhonov constraints which are the best possible expression of how we think heterogeneity prevails in the subsurface. That is up to us. That is a responsibility that we cannot escape when we're trying to solve an ill-posed inverse problem. However, we can look at it as a responsibility, or we can look at it as a mechanism for guiding the inverse problem to a solution that is a good solution, because this provides the mechanism where we can have a say in the estimated parameter field. And this is important. One of the beautiful things about Tikhonov regularization is the way it leaves our expression of expert knowledge to have an important part in how that inverse problem is solved. And this is important to achieving a solution to that inverse problem which makes sense. So from this series of slides we can conclude that the type of regularization that we use is important. We have a responsibility here to pose that inverse problem through the application of Tikhonov regularization in a way that gives rise to a solution that is good, taking in the definition of good, taking into account what we know or what we suspect about conditions under the subsurface. Tikhonov regularization allows us to do that. And secondly, as said previously, it's that last 5 to 10% of achieving a good fit that can do most damage to the parameter field that is estimated through solution of the inverse problem. So often we are entitled to get a good fit with the data, but the difference between a fit which is good and that which is too good might only be a small drop in the measurement objective function, but that last small drop can do an awful lot of damage to the estimated parameter field. Finally, it's worth noting that you can draw an L-curve yourself by running PEST in Pareto mode. Finally, I want to present a sequence of slides which are illustrative of what happens when we solve an inverse problem in general, and what happens when we solve that problem using Tikhonov regularization in particular. Some of these slides have appeared in other videos in this series. This is a synthetic case. I have a rectangular model domain. Water flows in at the top of that domain to a fixed head boundary at the bottom of that domain. I release a particle somewhere near the top. It flows through the porous medium to the bottom of the model domain. It flows through a heterogeneous medium, hydraulic conductivity field, which I've generated using a multi-Gaussian random parameter field generator. This is what that parameter field looks like, with higher Ks, higher hydraulic conductivities being indicated by blue areas, and lower hydraulic conductivities illustrated, demarcated by green areas. Using ModFlow, in this case, is my model, and using that hydraulic conductivity field I can calculate heads throughout the model domain. I can then use those heads as a calibration data set to infer a parameter field, and then I can make a prediction of particle travel time and emergence location using the calibrated parameter field. I can compare what I predict from the using the calibrated parameter field with the right answer calculated using the true hydraulic conductivity distribution. So that's the correct answer. That's how long it takes the particle to arrive at the bottom of the system. This is where it emerges, 206.78 meters from the western side of the model domain. So let me first calibrate this model using 84 head observations. So here's reality, and here are the correct answers for the time it takes for the particle to reach the bottom of the system and for where it emerges from that system. If there's no noise in the data, I can use Tikhonov regularization to solve that inverse problem, and I obtain a smooth parameter field which retains a lot of the detail of the true parameter field because there is a lot of information contained in 84 head measurements. Furthermore, because there is no noise associated with those head measurements, my target measurement objective function is 0. So I get as much information out of those 84 head measurements as is contained within those 84 head measurements, because that information is not contaminated by measurement noise. Nevertheless, I'm still lacking a lot of detail. The difference between this and this is significant, and because in particular the particle emergence time is sensitive to that detail, this calibrated model gives an incorrect prediction for that particle travel time. Does this make the model bad? Not at all. As we've discussed in other videos, it's not a calibrated model is not going to give us the right answer, particularly when the calibration process requires that an ill-posed inverse problem be solved. A model is bad when the uncertainty limits calculated during that model, the predictive uncertainty limits, do not encompass the right answer. In other videos, we'll discuss calculation of predictive uncertainty limits. If we do calculate them for this particular model, the right answer will lie within those limits. So this is not a bad model just because for this particular random parameter field, the calibration process gives predictions which are significantly different from the right answer. That's just what happens solving an ill-posed inverse problem when we calibrate that model. So now let me add some noise to the data. When I do that, my target measurement objective function is higher. In this case, I set that target measurement objective function at a value that recognizes this amount of random noise associated with those 84 head measurements. What's apparent is my capacity to infer detail is dwindling as there's more noise associated with the data, and for this particular prediction, which is sensitive to the detail, the calibrated model gives a prediction which is more incorrect than previously. And as I add yet more noise to the calibration data set and raise my target measurement objective function accordingly, I infer even less detail, and this prediction becomes more and more incorrect. Now let me repeat the process, but this time without any noise in the data. I will still use Tikhonov Regularization, using a covariance matrix, using a QR matrix, a weight matrix that actually is based on the covariance matrix that I use to generate my random parameter field. So everything is happening in a theoretically correct manner. So I'm using Tikhonov regularization based on the correct specification of heterogeneity as exists under the surface. So I can claim that the solution to my inverse problem is of minimum error variance. In general, we will not know the correct covariance matrix of reality. In fact, reality will be far more complex than can be expressed with a covariance matrix. But in this synthetic case, I've done everything correctly. So 84 head observations, 42, 24, 18, 12. Here's reality. Here's the exit time, the exit point, the correct answers. And as I now, with a sequence of slides in which my target measurement objective function in the Tikhonov-based solution of the ill-posed inverse problem, my target measurement objective function is 0, I can infer less and less detail of reality when I solve that inverse problem based on less and less data. As a consequence, in this particular case, my prediction of interest becomes more and more incorrect, but as stated previously, this is really not a problem because when I quantify the uncertainty of that prediction, it will lie within the uncertainty interval which I quantify in that way. So let's conclude this video. This video has been about Tikhonov regularization. And as I hope you've seen, Tikhonov regularization provides us a very flexible pathway to solution of an inverse problem that provides a solution that's in maximum accord with expert knowledge. However, the most we will get out of solution of that inverse problem, regardless of which regularization method we choose to achieve uniqueness, we will never see reality through solution of an inverse problem. The parameter field which emerges through solution of a non-unique inverse problem will always be a subdued form of reality, and the connection between the parameter field that we estimate and the parameter field that exists in reality is expressed through a resolution matrix. In practice, we don't calculate that resolution matrix, but we must calculate the uncertainty of predictions of interest if our model is being used to support decisions. Tikhonov regularization is a particularly nice way of solving an inverse problem, because the inverse problem is formulated such that what we see emerge through the calibrated parameter field is the heterogeneity which must exist to explain the data. The constrained minimization problem that we use to solve the inverse problem specifically says, I don't want any more heterogeneity expressed in this parameter field than that which can be supported by the data. Because of this, we don't see reality. Reality is not ours to know. We only see as much of reality as there is information content in the data to support it, and as there is information content in our expert knowledge, which we use as a basis for filling the T matrix, which is at the heart of the Tikhonov solution process to our ill-posed inverse problem. Thank you.